Welcome back. Our next speaker is Milica Vulic. She's a PhD candidate for zero-knowledge proofs at University of Novi Sad, Faculty of Technical Sciences. And Milica will present today the advancements in cryptography and zero-knowledge proofs, diving into the latest breakthroughs in zero-knowledge cryptography. As a PhD candidate, her research provides a unique lens into how these advancements are shaping the future of secure, scalable blockchains applications. Welcome, Milica.
Thank you very much, George. Hello, everyone. So as George presented, I'm doing my PhD in ZK at Faculty of Technical Sciences in Novi Sad. I would like to skim through my people here and see who heard of zero-knowledge proofs. Okay, that's great. Usually I don't see many hands, but the number we have here is actually really positive. Underlying of zero-knowledge proofs, there is lots of cryptography, and we'll speak about it very shortly. And guys, please bear with me because I suffered severe food poisoning in DevCon, so I'm barely standing, so that's why people brought me these chairs. As we know, with all those devices we use on a daily basis, they basically, all of them, they use cryptography. Wherever you visit a website that does not say this is not secured, it's using elliptic curve cryptography or something beneath it that can tell you that the website or material you're accessing is actually genuine. So yeah, cryptography secures the digital world, and that's how you can exchange messages with your loved ones without anyone interfering. And I'd like to present some advancements in cryptography that I've seen that I think they're really, really important, such as Binius curve. So yeah, cryptography started with, I think the earliest we can see is with Roman Empire during the Caesar's times, when they used Caesar cipher, and that's actually movement cipher where you definitely rely on the key, and that's how you move, and that's how generals actually were able to know that the messages they received were genuine, and they could communicate without their communication being intercepted or tampered with. So yeah, since, I don't know, more than 2,000 years, humans, they want to have secure communication and on the longer distances, so that they know that that cannot be tampered with and that they know that's genuine. Later on, of course, wars, they did a lot of revolution in the space of technology. So during the World War II, we had Enigma, for example, and that was, of course, being solved too. But that was the most complicated system at the time. And that was not enough. So we ended with Rivest-Schellmeyer, Edelman, and Diffie-Hellman key exchange systems. And RSA's limitations due to large key sizes and computational inefficiencies highlighted the need for alternatives, which we're going to speak later on. So that's how we got and ended up with elliptic curve cryptography, which is widely used right now. So it provides quite much stronger security than RSA, because they need smaller key sizes, because basically RSA is actually relying on integer factorization, where you have elliptic curve problems, which are much harder to solve on elliptic curve side. And so, yeah, whenever we design some sort of a system, we design it in a way that can be used on wearable devices and that we can have it portable without using too much space or too many like channels and energy consuming in the end, because we all know that there is like a battle for either more space or more energy. So today's challenges in elliptic curve cryptography, and like, because you actually came here to see and to hear about Binius curves, so I have to, tell you how we came there. So it's vulnerable to side channel attacks. So it's you can do analysis on timing and power, especially when it comes to different computational techniques. So sometimes there is a lot of computational inefficiencies, and there is like multiple curve standards, and with that you have to do a lot of interoperability, which results in a lot of with a lot of computation. That's just additional step you have to do, and sometimes then those systems, they just do not go, they do not advance as we would like to. So what is Binius curve? Yeah, that's something that's what I'm really excited about. So it's modern cryptography development that's following elliptic curve, elliptic cryptography principles. And for one, it's operating in binary fields. So that's something new. Usually we had only elliptic curve spaces, but now we also have binary fields. So it's optimizing computation over traditional finite fields. And when you're working in finite fields, you actually have to stay within it. That's why they're finite, right? So you have to do a lot of computation to stay within it, and a lot of modular arithmetics. And that's just not that fun if you have binary fields that you can use. So yeah, it's designed to overcome elliptic curve cryptography's limitation when it comes to speed, security, and efficiency. So what are binary fields? Who knows about binary fields? Does anyone know about binary fields? Okay. So binary fields are something that's dating back from digital electronics, where they had zeros and ones. Basically, you have binaries everywhere. Like you have to turn on and off the light, right? And you have like, that's like basically 0 and 1. It's either on or off. So you're using it every day. So there are teeny tiny, small binary fields, like field of 2, and that's really great. So you then have to have 256 bits, big numbers of fields. So yeah, like because they're very native to electronics and computation, and what we're using in all of the devices, and basically all of the electronics, except some of the analog electronics we're using in some music equipment like Marshalls. That makes them ideal for hardware implementation. So multiplication and addition in binary fields, they actually require less resources, because you don't have to do a lot of conversions, and they're practically native within their own field. And of course, there is a lot to say about security, because you have uniform computation, and that's basically lowering the risk of attacks, because you cannot do those side channel analysis, which you can see when something takes more timing to compute, or more resources. So basically, like everything you do within the binary field, you will end up with constant, either constant size or constant timing, but usually you will have both. And of course, you will have less memory usage and faster processing as the end result of it. So, how can Binius curve improve on elliptic curves? So, they can make encryption and decryption faster due to their nature of binary fields using them. Uniform point doubling in addition, and enhance resistance to attacks. And they're compatible with existing cryptographic protocols. And of course, they're improving performance as well. So where do we see practical applications of the Binius curve? So I could tell you like numerous ways that I see how Binius curve will improve, especially blockchain, Web3 world, how we like to call it, and zero knowledge proofs, but that would be really lengthy. You didn't have time for that. So, but what I can tell is that zero knowledge proofs generation that can be costly, and that can be quite slow. And especially when we're talking about rollups, because we designed that ZK rollups on top of L1 chains mostly, we wanted that to use because we wanted L1s to be faster and cheaper. But then we ended up with big zero-knowledge proofs and lots of time for them to be produced. So we were not happy too much about that, so people were trying to find new solutions, and frankly, I think Binius curve can help a lot on it. So how can Binius curve help? Well, it can model the most efficient way to generate and verify zero-knowledge proofs. And yeah, it can reduce computational overhead, leading to faster verification times in decentralized systems. And yeah, like you can use zero-knowledge proofs in not only in Web3, not exclusively tied to blockchain, but you can use zero-knowledge proofs to, for example, prove to your government that you voted without revealing who you voted for. Or you can prove to, let's say, the security guard in the club that you're practically over 18 years old without revealing your full details on your ID card. So guys, if you have any questions, I'll be around, and if you want to stay in touch, here are my socials. So thank you so much.
Thank you, Milica. Any questions from the audience? Yes? No? Going once, 2 times, 3 times. Thank you.